All right, guys, so today we're starting in with Chapter 8, Section 8.1. As you can see, we've got matrices and systems of equations. So there is a definite connection between Chapter 7 and Chapter 8. Chapter 7 was all about systems of equations, and now here Chapter 8 is all about matrices. Maybe I'll ask, how many of us feel like you hear the word matrix or matrices and we know what we're talking about? We remember this from previous years. Yeah, maybe you needed to see one. There's some matrices right there. Okay, some of these things that we're talking about, these are matrices. Now, what I don't know, honestly, but I'm going off of what students have told me in past years, is that in past years, there was never really a connection made between matrices are really just a way of writing out systems of equations. Okay, so like I said, maybe some of you are like, yeah, of course, that's definitely what Algebra 2 teachers were talking about. But in most years, when I say that, students are kind of like, wait a sec, hold on. These are connected? These are the same thing? And the short answer is yes. So if you recall polynomial long division, okay, again, just making this up. 5x to the fourth minus 7x cubed plus 3x squared minus x plus 5 again. And we're dividing this by x minus 3. Okay? Everybody remembers doing this stuff? We really loved it, if I recall. Again, like this was definitely a top 10 thing that we did so far. Favorite thing in all of math. Well, what I would assume is that everybody would look at this and realize, okay, my divisor's working out pretty nicely, and we're going to turn this into a synthetic division problem. So 5, negative 7, 3, negative 1, 5. Now, why is it that we all, well, first off, am I assuming correctly that we would prefer synthetic division over long division? Okay, now why would we prefer synthetic division over long division? Get rid of all the x's. Exactly. Guys, do we realize that's what matrices do? Okay, if we have a system of equations, if it's set up properly, which, you know, good news, if you've been wondering, why is Mr. Clemenger such a jerk about this? Everything has to be in standard form. Okay, why can't I say that y plus z equals x plus 1? No, it's not in standard form. It's got to be in standard form. The reason is because where we're going with matrices is that if you're not in standard form, your matrix doesn't work. Okay, so instead of trying to say, all right, now that we go to the next chapter, let's start practicing putting it in standard form, we just do that from the beginning. Okay, so hopefully by this point, it's not weird, it's not abnormal. In fact, at this point, I'm hopeful that if you saw an equation or a system with the equations that were not in standard form, that looks weird to you. And I think that it would. I think that most of us be like, wait a second, I've got to get this x shifted over, or I've got to move this constant or whatever needs to happen. Okay? But I completely agree that, to me, synthetic division just looks cleaner, it looks simpler, it looks like we can just focus on the numbers, and that's what matrices do too. Okay? If we can create a matrix out of a system, there's a lot that we can do with it then. And then the other gigantic advantage is that if you've got one of these graphic calculators, you can pretty much just push in, type in a couple of buttons, or punch a couple of buttons, after you type in these matrices, and we can solve a lot of the matrix stuff on the calculator, okay? So you know where we're at right now, quite frankly. A lot of this, yes, we're going to show you how to do it on the calculator, but we're going to have to do it by hand. So the stuff that we're doing, it's, again, the reason why we're introducing it this way is that if you feel like you have a future in mathematics, like to where you're actually going to be doing some of this applied math stuff, I'm talking long term, like down the road, like into college, things like that, you're going to be working with matrices a lot. Like it's going to be a big part of it. The good news is that matrices, once you get the hang of it, once you understand how to build them, the rest of it's pretty simple. The other thing that's going to be pretty gigantic for us in terms of what we can accomplish is that if you think about it, if we have a system of equations over here and then we have another system of equations over there, there's a lot of mathematical value if we can multiply them together or if we can add them together or something like that. When we have them in system form, that doesn't even seem comprehensible. But as soon as we put these in matrix form, now all of a sudden there's a lot of mathematical things that we can do with them, and there's a lot of value to be had. All right? So the goals that we have here for section 8.1, as you can see, students will be able to write matrices and identify their orders. I think that again, maybe after just seeing even one example, this is going to come back to you. But this was definitely something that we were doing in Algebra 2 last year. This is one of the biggest concepts, frankly. Number 2, students be able to perform elementary row operations on matrices. Goal number 3, students be able to use matrices to solve systems of equations. This is going to be a work in progress for sure. You're going to notice this goal shows up in multiple sections. We're going to be using matrices to solve systems of equations. In fact, I would say that's the biggest number 1 goal that we have for Chapter 8 is can we use matrices to solve systems? That's where we're at. Okay. Again, thinking big picture again. A lot of us, some of us are finished with it, but a lot of us have the ACT ahead of us, and that's going to be advantageous to score as well as we possibly can. If you're thinking that, all right, I'll probably be the lucky one to get an ACT that doesn't have any systems of equations, you are fooling yourself. There will be systems of equations on the ACT, not just once, probably 7 or 8 of them, or at least problems to where you could set up a system. And if we figure out how to do this, turn a system into a matrix, and then we can do all the work on the calculator. Remember, the ACT is a speed game. So, again, that may be playing into our favor. All right, so we're going to show you how a lot of this stuff works. But again, using matrices to solve systems. Now, one thing that I do want to point out, something that's going to be completely brand new, are these elementary row operations. So usually, I don't know, I feel like a con man or something like this, the way that I'm going to say this. But usually you hear me say it all, and I'll probably say it 3 more times in today's lesson, that in pre-calculus things sound more complicated than what they really are, right? Goal number 2, we're going to perform elementary row operations. This is one of the only times that we have to report. This makes it sound a whole lot easier than what it actually is. Okay, as soon as we start saying elementary row operations, I think just that word elementary, we start to, it just sort of comes over us that, all right, this is easy. This is like little kid stuff because it's elementary. They're not super difficult, but I just want you to know going into it that this is going to be new. So today it's going to feel kind of weird. Also, Chapter 8 is unique in that, wanted to show you guys this one. Chapter 8 is a little unique in that usually math is such a progression, and again, that kind of in theory means that section 1, not so bad, and then we do a little bit more in section 2, a little bit more in section 3, a little bit more in section 4. By the end of the chapter, it's like, yeah, we're doing pretty complex stuff. That's exactly how Chapter 7's model was, right? Chapter 8 is pretty different. I would make the argument that the hardest section in Chapter 8 is section 8.1, okay? So it's like, you're going to feel like you just get punched in the stomach, and then section 8.2, it immediately gets really, really simple. Okay, so I guess what I'm asking you to do is don't quit on Chapter 8. Don't feel like Chapter 8 is the worst thing in the world. I can't figure out matrices because I struggled with Section 8.1. Please don't allow yourself to think that way. I just want to tell you right now that we're going to throw a lot at you here in Section 8.1, but you can handle this. You will be fine. You'll get through it. I'll make sure that you get through it, especially once we get into Section 8.2. Then it's going to be a whole bunch of that. Can you take this matrix and add it to that matrix, and it's going to start to feel, like I said, really familiar and simple, things like that. All right, so this is where we're going, though. Can we solve a system using matrices? Well, right now, we have too many questions to even start this problem, right? Are we even comfortable with how to create a matrix out of that system? Not yet, again, but we're going to show you how that works. Once we get this to look like what we call augmented matrix, all that we're going to do, just like synthetic division, we're just going to steal the coefficients. So that top line is going to be 1, 1, 2, 3. That middle line is going to be 3, 4, 4, 9. And that bottom line would be 5, 2, 15, 13. What's this weird dotted vertical line you have? Well, that's where the equal signs were. So again, this is what we call an augmented matrix. But even once we're here, do we know how to, it's not solved. We're going to have to figure this out. So what we're going to want to do is to put this into what we call row echelon form, which short answer is that we want to get positive 1s on the diagonal, and we want to get 0s underneath. Right now, clearly, we don't have that. That's where these elementary row operations are going to come in. We're going to have to do some type of combination. Row 1 plus row 3, or negative row 1 plus row 2, or, things like that. That's the type of stuff that we're going to have to do to create these 0s and 1s in the correct location. Because once we're here, we're going to have other numbers in all of these spots. and that's going to lead us to our answer. Okay? That's where we're going. I just wanted you to see kind of big picture. All right, what are we talking about? You probably also realize that in that even 60-second explanation, I used a lot of terms and phrases that you're not familiar with. So that's going to be a big part of Chapter 8 is that, yes, you've seen matrices, you've worked with matrices, but you really focused on the operations of matrices. Like how do you add them together? How do you multiply them together? And please understand that that is very important. I don't want to discredit that at all. But there's a whole nother level that we're going to go to with matrices. And a lot of it's going to be utilizing new terminology. So stick with me on the terminology, and we're going to make some sense out of it. So starts off pretty weird. This entire thing is actually the definition of a matrix. Like I said, it's a weird looking definition. But a few key points that we want you to focus on here. It says that if m and n are positive integers, okay, again, we can't have a fractional or a decimal number of rows or columns or things like that. So m and n have to be positive integers. Can't have a negative number of rows or a negative number of columns or anything like that. Okay? So if m and n are positive integers, the way that we read this, by the way, is m by n. All right, then the matrix is going to be what we call a rectangular array. Again, already using fancy talk. All right? Our values are, again, each of these numbers inside, we call them elements. Our elements are always going to be in a rectangular format. Okay? We're going to have a certain number of rows, we're going to have a certain number of columns, but it's always going to create a rectangle. Just the former geometry teacher in me has to ask, are squares rectangles? Squares are rectangles, right? So it's very possible. We call them rectangular arrays, but we could have a 3 by 3. And before we say, no, that's not a rectangle, it's a square. Squares are rectangles. Okay, just remember that going into it. All right? So each of these entries are elements. Like I said, this is directly out of our textbook. It's really not going to be much of an issue, but just so we're aware, like this one right here, it sure looks like A12. But what that actually represents, we would actually read that as A12. The reason is its location. That's what this is all about. It's in row 1, column 2. Okay? Or this one down here, it's not A32 necessarily, it's A32 because it's in row 3, column 2. Now what does that mean? Row 3. 1, 2, it's the third row down. 1, 2, it's the second column over. Okay, so just probably could go without saying, but I'm going to say it anyway to again, just in case if there's even one person out there who is shaky on it, we want to make sure that we have this down. Rows are horizontal, columns are vertical. Okay? We can't get that mixed up. We can't afford to get that mixed up because a huge part of practically every problem that we're going to be doing, one of the first things that you're going to be asked, either on your assignment or either by me in class, we see a matrix, what's the order? All that means is how many rows by how many columns. That's what we refer to as the order of the matrix, rows by columns. Because if we have a specific order, then that's going to lead us to be able to do something or to not be able to do something based on the order. All right? So a couple of these quick little definitions. Again, hopefully they make some sense here. A row matrix, it's going to be a matrix that has only one row. So if you had something like 1, 2, 3, there's a row matrix. Okay? Column matrix, I'm sure we can figure out it's going to be a matrix that has only one column. All right, yeah, 4, 5, 6, something like that. There's a column matrix. Well, once again, this is one of the most important terms that you're going to hear all chapter because this is going to show up in literally every single section. We need to care about the order of the matrix. The order is how many rows by how many columns. Okay, so a matrix having m rows and n columns is going to be of order m by n. If m and n are equal to each other, then we actually even call it a square matrix. Okay? So the example I used before, if you have 3 rows and 3 columns, 3 by 3, it makes a square. Looks like a square. We call it a square matrix. All right? So a little bit of practice ordering these things. What are you going to tell me on this first one? What's my order of this matrix in part A? 2 by 2. Good. We have 2 rows by 2 columns. Good. What about part B? Abnormal. This one doesn't show up very often, but technically it exists. It's a 1 by 1 matrix. What about C? 3 by 2. Not to be confused with part D. What's this? 2 by 3. 2 by 3. Now, we're using the X. We understand we're not really multiplying these, correct? We're not multiplying the number of rows by the columns or anything like that. This isn't a multiplication problem. And for that reason, we don't want you to make that fatal mistake of assuming that 3 by 2 is the same as 2 by 3. They're not. They each have 6 elements. I agree with that, but they